In this video, we're going to look at another application of work integrals. The gravitational force of planet Mars on a satellite of mass m at a distance of y meters from the surface of the planet is given by f of y is equal to km divided by r plus y squared. K is equal to 4.28 times 10 to the 13 meter cubed per second squared. K is really just equal to g times mass of the planet, which is Mars. So capital G is the gravitational constant of the universe, and capital M is the mass of Mars. We group these constants together to make our computations a little bit easier. All right. So capital R is the radius of Mars. That's 3.39 times 10 to the 6 meters. And part A of the question asks us to find the work required to launch this satellite of mass M into outer space. That means infinite height. Part B, find the escape velocity, VE, such that the satellite has sufficient kinetic energy at firing to supply the work needed to raise this satellite of mass m to infinite height. So let's do part A of the question. Find the work done to launch this satellite. So force is equal to F of y is equal to Km divided by r plus y all squared, where m is the mass of the satellite. So dw is equal to km divided by r plus y all squared times dy. Work is force times distance. Now we integrate, add up all the elements of work that's needed to launch this satellite from the ground level of Mars to infinite height. So work is the integral from y equals 0, ground level, to y equals infinity, infinite height into outer space, dw. So this is an improper integral. We're going to replace the upper limit by a different letter, like d in this case. So work is equal to, and take the limit as d approaches infinity. Integrate from 0 to d. And the dw is km divided by r plus y all squared dy. Let's apply U substitution. Let u be equal to the inside function r plus y. Differentiate both sides and we get du is equal to dy. Alright, so let's label this. This is an improper integral. The reason it's improper is because the upper limit of integration is infinity. Improper integral. Alright, so work is equal to limit d approaches infinity, integral from 0 to d, km, divided by r plus y all squared dy. Applying U substitution and integrating, we obtain limit d goes to infinity minus km divided by r plus y. And evaluate this from 0 to d. Work is equal to limit d goes to infinity minus km. Applying the fundamental theorem of calculus, put the upper limit d into y, so we get d plus y. So we get r plus d minus km divided by r plus 0. If we simplify this, we're just going to get km over r. This ratio approaches 0 as we take the limit d goes to infinity. That's very important, and that's because the denominator grows to infinity, so the ratio approaches 0 as the distance d goes to infinity. Alright, so when we simplify it, we get km over r, where m is the mass of the satellite. Alright, so k, the constant k for Mars, which is just g times the mass of Mars, that's 4.28 times 10 to the 13 meter cubed per second squared. These are the units. The radius for Mars is equal to 3.39 times 10 to the 6 meters. So let's calculate the work required to launch this satellite from ground level of Mars to infinite height into outer space. K times the mass divided by R. Well, K is equal to 4.28 times 10 to the 13 times the mass. We don't know the mass, and we just leave it as mass. That's just a variable, so to speak. So 3.39, that's the radius of Mars, times 10 to the 6. So the work done to lift this satellite into outer space is 12.63 times 10 to the 6 times the mass, and of course the unit is in joules. So we have the work in terms of the mass. That means if you have a satellite that weighs more, has higher mass, it requires more work to launch this satellite into outer space from the surface of Mars. So the work done is 12.63 million, approximately, million joules multiplied by the mass of the satellite. A heavier satellite requires more work, of course. All right, part B of the question asks us to find the escape velocity on Mars. So for the satellite to overcome the gravitational pull of the planet Mars and reach infinite height, the satellite must have sufficient kinetic energy at firing to supply the work needed to raise the satellite of mass m to infinite height. So kinetic energy is, of course, 1/2 mv squared. The strategy that we'll use here to find escape velocity is make kinetic energy equal to the work done. And we will solve for the escape velocity. So the kinetic energy is 1/2 mv squared is equal to 12.63 times 10 to the 6 times the mass of the satellite. Now something very interesting happens here. The mass cancels. The mass of the satellite cancels. That means the escape velocity is independent of the mass. The work done to lift the satellite from ground level of the planet to infinite height depended on the mass, of course. You can see that here. It is 12.63 times 10 to the 6 times the mass of the satellite. But the escape velocity does not depend on the mass. So we're now going to solve for the escape velocity. That's just algebra. V squared is equal to 12.63 times 10 to the 6 times 2. And let's take the positive square root. So V squared is equal to 2 times 12.63 times 10 to the 6. Taking the positive square root, the escape velocity is approximately 5,025.93 meters per second. Now let's change these units to kilometers per hour to get a better sense of how fast the satellite has to be fired from the surface of the planet to escape the gravitational pull of Mars. 5,025.93 meters per second times 1 kilometer, there are 1,000 meters in a kilometer, divided by 1,000 meters, times there are 3,600 seconds in an hour, 3,600 seconds in 1 hour, and we cancel things out. Meter cancels with meter, second cancels with second. If we simplify this, the velocity comes out to be approximately 18,993.36 kilometers per hour. So the escape velocity has to be, of course, higher than this because there's frictional losses as well. So the escape velocity must be at least as large as this amount to escape the pull of Mars. 18,093.36 kilometers per hour. That's the escape velocity on Mars. All right, thank you.